Have you ever wondered how a tiny little software bug, something as simple as a program crashing, can be twisted and turned into a weapon? Well, today we're going to pull back the curtain on the anatomy of a digital heist. We're going to show you step by step how an attacker can go from a simple crash to taking complete control of a system. Right. It all starts with this one little question. We've all been there, right? A program freezes, it crashes, you get the spinning wheel of death. But what if that crash wasn't random? What if it was engineered, deliberately triggered to act like a key turning in a lock? And that leads us right into the first phase of our operation, understanding the vulnerability. See, we're not talking about just any old bug here. We're looking at a crash that has a very specific, very malicious purpose. And it all revolves around something called a stack overflow. So, try to imagine the program's memory like a neat stack of plates in a cabinet. Normally, everything has its own spot. But our attacker, they don't play by the rules. They send in a huge amount of data, way more than the program was built to handle. And this data, it overflows its little plate, spilling all over the other plates in the stack. And here's the critical hit. It overwrites the return address, which is basically the program's GPS, telling it what to do next. Just like that, the attacker has ripped out the program's roadmap and is about to draw in their own. Okay, so the attacker has control of the wheel. They can steer the program wherever they want. But where do they want to go? They need a tool, a custom-built package of instructions to get the job done. In the world of hacking, we call this the payload. And this payload, it's not just a bunch of random junk. Oh no, it is a work of art, in a devious sort of way. It's this meticulously crafted sequence of ones and zeros, kind of like a safecracker's toolkit. And it gets sent right through the front door disguised as normal data. It has three key parts we need to understand. First up is something called the NOP sled. The best way to think of this is like a long, slippery landing strip for an airplane. NOP stands for no operation. It's an instruction that literally tells the computer, hey, do absolutely nothing. Just slide on down to the next instruction. By making a long chain of these, the attacker gives themselves a huge target. Even if their aim is a little off, the program's execution just slides right along the sled and into their trap. So after that landing strip, we hit the shellcode. This is the main event. It's the heart of the payload, the whole reason for the heist. This is the code that actually does the dirty work. Maybe it deletes files, maybe it creates a new user. But most of the time, it spawns a shell. And a shell is just a fancy word for a command prompt. Getting a shell is like being handed the keys to the entire system. Game over. And finally, we have the new return address. This is that malicious GPS coordinate we talked about. The attacker calculates this address with extreme precision, so it points somewhere on that big, slippery NOP sled. So when the poor, confused program tries to figure out what to do next, it's sent right to the attacker's landing strip. So when you put it all together, you can really see the genius of the structure. It's this very specific sequence. You've got the long NOP sled to act as a forgiving target, then the shellcode with the actual commands, and bringing up the rear is that hijacked return address that kicks the whole thing off by pointing the program right back to the attacker's code. But hang on a second. How in the world does an attacker know exactly how to build this thing? I mean, they can't just guess, right? Nope. This part requires some serious detective work. It's time for some reconnaissance. And it's a really methodical process, almost like a checklist. First, they have to find the offset. That's the exact number of bytes of junk they need to send to perfectly overwrite the return address. Then they get their shellcode ready. After that, they need to figure out where in memory their payload is going to live. And only then, when they have all those pieces, can they assemble the final weapon. So how do they find that all-important offset? It's actually super clever. They don't just throw a long string of the letter A at the program. Instead, they send a unique, non-repeating sequence of characters. It's called a cyclic pattern. So when the program inevitably crashes, they can look at the exact characters that caused the crash and calculate the distance to the return address down to the single byte. It's surgical. And for this specific program we're dissecting, after all that detective work, what's the magic number? It's 140. 140 bytes, not 139, not 141. It has to be exactly 140 to hit the target. All right? Now that they have that magic number, that critical piece of intel, the attacker can head back to the workshop. The recon phase is over. It's time to build the weapon. And you know what? The math here is actually pretty simple. They know the total space they need to fill before the return address is 140 bytes. They also know their shellcode is 24 bytes long. So what's 140 minus 24? That gives you 116. And that is exactly how long their NOP slang landing strip needs to be. And there you have it, the final blueprint. It's 116 bytes of those do-nothing instructions, followed by the 24 bytes of actual shellcode, and then it's all capped off with that 4-byte malicious return address that starts the whole party. The tool is built, it's armed, and it's ready to go. Okay, so we've seen the weak spot, we've seen how the tool is built, we've done the recon, now for the main event. It's time to launch the attack and see if this whole digital heist actually pays off. On any normal day, you'd run this program with a simple, harmless argument, but not today. Today, that normal input gets replaced with our massive, carefully constructed payload. It looks like a long, ugly string of computer code, but to the vulnerable program, it's just another piece of data. This is it, the moment of truth. And bam, success. The command runs, but look what happens. The program doesn't just finish, it doesn't crash in a messy way. Instead, a new command prompt pops up. That shell 5.1 that's not our prompt. That's the attacker's shell, the one spawned by their shellcode. They are in. The system now belongs to them. So we just walked through this entire heist on a simple, kind of broken little program. But it makes you think, doesn't it? If this is what's possible on this tiny scale, what does that mean for the incredibly complex software we all rely on every single day? Your operating system, your web browser, the apps on your phone? It just goes to show you, sometimes the smallest crack in the foundation is all a thief needs to bring the whole house down.